So for this last experiment about PID controllers, the main goal here is to understand how different controllers such as the PI, PID, and PD controllers work and how it affects the response of a given plant. And for this experiment, I used the given plant transfer function and I applied the controller design concepts using proportional gain compensators. So for the first part, I designed the PI controller using a proportional gain of K, which is equal to 3.3, and the compensator A of S is equal to S plus 1.3 over S. Over the simulation output, I recorded the damping ratio, natural frequency and settling time, the peak time, and the percent overshoot. The controller function became 3.3 S plus 4.29 over S, which shows that it behaves as a PI controller. So this page shows the manual computations based on the closed loop poles. I solved everything for the natural frequency, the damping ratio, the settling time, the peak time, and overshoot. One thing also notice that the computed values are also close to the simulation values, which help me confirm the relationship between the pole locations and the step response behavior. So for the next part, I tested another compensator with a proportional gain of 0.48. This controller has an additional 0, so it behaves like a PID controller. And compared to the PI controller, the PID controller actually gives more control over both transient and steady state response. So in this experiment, I chose PID controller because the derivative term helps improve the transient response, while the integral term helps reduce the steady state error. And this page again shows the derivation of the PID controller transfer function and the step response parameters. And the PID controller was written as 0.48 S plus 3.8544 plus 6.4702 over S. And from the calculations, the damping ratio, natural frequency, settling time, peak time, and overshoot were determined using the closed loop poles. So this page discusses mainly about the PID and PD controllers. The PD controller only has a proportional and derivative action, so it does not have an integral term. Because of that, it cannot satisfy a design requirement that needs a zero steady state error for a step input. And the root locus and step response also show that the system is stable because the closed loop poles are in the left half plane. And for the final part, I also implemented the PID controller using a operational amplifier. The circuit relationship shows how the resistor, capacitor, and values respond to the proportional, integral, and derivative gains. And here this helped connect the mathematical controller transfer functions to a possible circuit implementation. So one challenge of this entire lab experiment I experienced in this was understanding mainly how the compensator transfer functions becomes PI or PID. Another challenge was also like connecting the root locus results with the step response graph and also the manual computations. And my note to self is to review how the poles how the pole locations affect the damping ratio, settling time, peak time, and overshoot, because these values are very important when designing controllers. And overall, this experiment helped me understand that controller design is not only about a stable system, but also about improving the system's response based on the required specifications.